There are two primary methods for optimizing systems of differential and algebraic equations. We're going to be talking about a simultaneous optimization method with orthogonal collocation on finite elements. So methods for optimizing DAE systems, you have the first one, which is a sequential approach. This is called a single shooting method, where we solve the objective function and the model equations separately and successively until we converge to an optimal solution. Simultaneous method is where you solve the objective function and the constraints together, and you solve the constraints, the model equations, once as they converge to a solution with the objective function. And then multiple shooting method is a hybrid method between a single shooting and a simultaneous method. Alright, so I'm also going to give an overview of orthogonal collocation on finite elements, and we're going to do a simple calculation just to show the method. So when we talk about technologies like model predictive control, you might have a manipulated variable like the reflex ratio that determines how much goes back to the column versus is produced as distillate. As the reflex ratio increases, you get more recirculation and you get higher purity distillate, but not as much. And so this is the primary manipulated variable. Now you might have as your controlled variable, the one that you're trying to drive to a set point, it would be the target composition coming out of the column. And you need to maintain that by adjusting the reflex ratio continuously because there are disturbances to your process. So when we talk about optimizing this, you have all of the states, x1 through x30, also the bottoms composition and the distillate composition, and you might have a mathematical model of some sort that relates the reflex ratio to the distillate purity. All right, now once we have those equations, that might be from model identification, it might also be from physics-based representation of the system, or a hybrid between the two. Once you have that model, now we want to apply it to optimize the reflex ratio to get the purity that we want. So if we talk about these three methods, sequential shooting and this hybrid sequential simultaneous, which we also call multiple shooting, or a simultaneous direct transcription or collocation methods, we have all three of these that we can use to do this optimization. When we talk about model predictive control, here's the current time, and we're projecting forward into the future. This is the solution of our equations, whether it be a finite impulse response model, an ARX model, some kind of time series model, or else a physics-based dynamic model. This is the reference trajectory that we want to try to drive to. And then we have our manipulated variable move plan. So each of these are decisions that the optimizer can make, deciding whether it wants to move it up or down to get it as close as it can to that reference trajectory. So in this case, this would be our reflux ratio, and this would be our concentration of the distillate. All right, so we talk about sequential or single shooting method. It's like you have a guess on the reflex ratio, and you figured out that maybe you're too high. So you have another guess, and maybe you're just a little bit too low. And so you continue this process, getting information about whether you guess too high or too low and make those corrections. So in this case, you're evaluating the model equations and the objective function separately. In this case, the objective function is how close you're getting to the target set point. So you do that over and over again, optimizing and minimizing maybe a sum of squared errors between your trajectory, CV sub t, and the CV, the predicted value. And you're going to be between 0 and 100, let's say, on the reflex ratio, subject to the dynamic equations. Now when you talk about multiple shooting, it's like single shooting, but you've broken it into segments. And that the end of one segment has to equal the beginning of the next segment. So you keep doing this and guessing and checking on the reflex ratio until you get as close as you can to the optimal solution. All right, same equations that you're solving, but now you have this sequential MPC that can adjust. You might have a black box model. Let's say if you want to use a sequential method, it's very good if you don't necessarily have the equations or the equations are too complicated to solve simultaneously with the objective function. So also you get feasible intermediate solutions. So you can iterate for 10 cycles and your solution is going to be feasible. You can stop and then iterate some more and then stop again, kind of as a checkpoint. Now in this case, you use sequential when the number of manipulated variables is small. It's not a very fast method, and also time horizon has to be short. You can't make too many decisions going off into the future because it takes too many perturbations of those to find an optimal solution. It's also very valuable to use this method if your state dimension is large. Let's say your model is described as a partial differential equation, then a sequential method might be the best. Now here's some source code if you want to try to implement that. It uses the SciPy package for minimizing to optimize your future trajectory. Okay, so you don't necessarily need gradients from your model. You can just get the objective function and evaluate that repeatedly over and over again, also solving your model as well to feed into that objective function. Okay, simultaneous optimization is different than those two. We are going to be solving the variables and the equations, the equations and the objective function simultaneously, minimizing the objective function and solving these equations. So when you solve the equations, you're only solving them once and you solve them at the optimal solution. It takes a little bit more to set up this approach. We're going to review how to do that today. Same equations that we're solving, it's just we transcribe the differential equations into algebraic equations. And then it gives very fast. You can do it for many MVs, many degrees of freedom. Also for unstable systems, it's better for unstable systems like if you had an inverted pendulum, for example, or others that you don't necessarily track to a steady state value with a particular manipulated variable input. All right, so also the other issue with this, unlike the sequential approach, is that partially computed solutions, if it hasn't finalized to the convergence criteria, they're not going to necessarily be feasible solutions. So you can't use kind of an early stopping criteria. Also, this is good if the time horizon is long, the state dimension is relatively small, not like solving hundreds of thousands of differential equations, because you're putting everything on this whole time horizon into a single solution, and the computer has to solve all of those equations and variables together. And we'll see that there's some source code here with the temperature control lab that replicates what we did here. All right, so simultaneous optimization, we're going to take this system of equations and transform it into an algebraic form. So you've transformed f of CVMV into g of CVMV, and you can see there's no differential on the left side. So here we've transformed this from a differential equation into an algebraic equation. So that's the only thing that's different about these two, and we're going to use something called orthogonal collocation on finite elements in order to do this transformation. And then we also need things like automatic differentiation to make this fast, and also large-scale nonlinear programming solvers that can solve these larger problems. Also, this is going to be facilitated with Gekko optimization suite. I'll show an example of working with that. Okay, so what we do, let's just show this for one time step here, where we have x of t is going to be a polynomial approximation to these time points to the solution of the differential equation. Now we select the different time points based on Lobatto quadrature. You can also do Radau quadrature or others that are orthogonal points where you get the best the best spacing of these time points to get the best accuracy for this approximation. Okay, so we're only going to be evaluating the equations at particular points along the way, and these time points are placed optimally to give us the most accuracy with the fewest amount of points. All right, so what we're going to do is relate our derivatives to our state values, because we need the derivative values here, here, and here. All right, and we're going to relate that with this matrix M. And what we do is we substitute in this x of t into these equations. So we take the derivatives. You can see this is the derivative of x of t. And here we have x1, x2, x3. We've substituted those in and then subtracted x naught, which is going to be equal to a. So that's why you don't see the a here, is because you subtracted off the initial condition. And then it's just a matter of plugging in these time points. They're given by a Lobatto quadrature, and then coming up with your matrix M. So we've just substituted in all these t values and just computed that matrix M. And then the other thing that we do to make this easier to solve, instead of putting M on this side of the equation, we just move it over to the other side of the equation, basically by taking the inverse of M. That becomes n. And that's going to be a 3 by 3 matrix. So this is, if you go to time equals 1, you just use the n matrix. But let's say you go to time equals 2, from 0 to 2, then you just put in 2 there for the time. Okay, so that's the derivation of this. Here's the n matrix based on Lobatto quadrature. Okay, and we've fundamentally just fit a polynomial to those points. All right, so the first one, we're going to solve this differential equation with 4 nodes for t equals 0 to 1 with y naught equals 5. Okay, so we're going to first of all identify the 6 unknowns at the node points. All right, there are our 6 unknowns. Then we want to list the 6 equations. This is going to be 2 for each node. Okay, so there are the 3 equations, and then the next 3 are right here from the orthogonal collocation. All right, there's our n 3 by 3, and then we'll solve the 6 equations and 6 unknowns. And there's going to be a Jupyter notebook. So we have these 6 equations right here, 6 unknowns, and we're going to set that up and solve it. First of all, we're going to do it with Gekko and then just compare it with Fsolve. Okay, so let's go ahead and solve this. All right, this Jupyter notebook that you can see from the link, you're going to open this up. You can either open it with Google Colab, and I'll just show you the page here. Okay, so it's right here. I'll put this link in the description. And okay, so there's the URL. You'll have that in the description below the video. And you can select it, and then you can either come here to Google Colab, and this lets you run it just through a web interface. You don't need to install anything, and you can type in your code here if you want to. Or you could download the Python notebook, the Jupyter notebook from GitHub, and I'll just show you that as well. You can get both notebooks from GitHub, and there is the solution as well if you need that. Okay, so here's ours right here. You need to download this, and then you can run it locally. All right, so now what we want to do is just solve the equation with nodes equals 4 at time points 0, 1, 2, and 3. All right, we're going to solve this one first. It's like we're solving those first 4 and then stitching another 4 together and then another 4 together as well. We'll start with initial condition of y naught equals 5, and we want to also show the internal node solutions. All right, so let's go ahead and just start. We'll just do from Gekko. Let me make this just a little bit bigger. All right, so from Gekko, we're going to import Gekko. That's the first thing we need, and then we want to create a new model M. and we're going to just create it with the Gekko command, and then we want to create our new variable y. Alright, so y is going to be this variable. We'll give it a starting value of 5 for the initial condition, and then the equation is going to be y dy dt equals minus y, or we could put plus y equals 0. Okay, so either of those work to define the equation. Now we need our time points. Alright, so I'm going to do m dot time equals, and this is going to be 0, 1, 2, 3, and then I need to just change some options. So I want to solve this in simulation mode, and that's going to be I mode 4. And then the next thing I need to do is just change the nodes. Okay, so nodes, I'm going to change that to 4 as well. Okay, so nodes equals 4. Default is 2 in Gekko. Alright, and then we'll solve it. Okay, so it's going to solve it, and Control Enter will solve it. You can see it took 1 iteration. These are linear equations, so it's going to be very fast. See how much time it took. There's no objective there. It's just simulation only, and it was successful in finding the solution. So I'm just going to turn off display so I don't see the output, and then I'll just insert a cell below, and let's just plot the solution now. So I'm going to import matplot lib.pyplot. I'll go ahead and import that as PLT, and then I will plot m.time and y. Okay, I can see the values integrated. I'll replace those with red circles. Alright, so you can see the solutions at 0, 1, 2, and 3. Alright, so now what I want to do is show the internal nodes. Now this is kind of gets down into Gekko, to be able to show some of these things that you don't normally see, some things that happen behind the scenes. So what I'm going to do is just turn on an option here. And this is going to be CSV write, and I'm going to turn that up to 1 additional level to 2. And then what I want to do is go ahead and just open the folder where Gekko is running, and also switch remote equals false, so it runs locally instead of on the internet. Okay, so when that executes, then I've got this temporary folder that just came up, and this is the run directory for a local solution. And I'm going to see results all. And that's not just going to be the values that are at the collocation nodes that I wanted to see, okay, the 0, 1, 2, 3, but it's also going to include at other times as well. So you can see it has 4 nodes, 0, and then 2 other time points that are in between it, and then you reach 1. You have the next segment that has 2 internal nodes, so there's nodes equals 4 for each time period that I requested. And then you can also see the value there. Now that's labeled v1. Makes it a little bit easier if you name the variable. So you see in the debug area, I'm going to put name equals y. And then when I run it again, then I open it, and I'll just open it with Notepad. Okay, so you can see now it's named it as y instead of v1. Alright, so there's my results file, but now I want to just read it back and be able to plot it in here to be able to see the results, all of them, not just the red dots, the ones at the end, but I want to see the 2 internal nodes as well. So let's go ahead and just import. I'm going to import JSON. I'll go get the JSON file that was in that directory as well. It's a little bit easier to import in Python this structured data that came from JSON, or you can do the CSV as well, either one. Okay, results underscore all dot JSON, and I'll open that as f. And then I want to do results. I'll just say r equals json dot load, and I'll have my file that I just loaded in. I'll load that in. All right, now I can plot. I can add to the plot. I can say this is going to be r, and I'm going to have time, and then I'm going to have r, and I'll do y as well. And let's do those as blue x's. All right, so I see my red dots here, but then I also see all of the other collocation nodes that span this time interval. Okay, so that is the Gekko solution. Let's do this one without the automated collocation. So Gekko is adding the additional collocation equations. Okay, we had this time interval defined. If we just set it down to one interval, okay, I only want to see one now, it's only going to plot these first four right there. So let's run this again. You can see the solution at these points. Okay, so we want to compare that Gekko automated way of doing the orthogonal collocation to something where we're not using Gekko to do that automation. So let's do that with Fsolve, and we're just going to solve these 6 equations and 6 unknowns. So I'm going to put this a little bit off to the side here. Let's see if I can get these equations. Okay, so these are my equations right here. Go ahead and close these screens. Okay, so I've got my 6 equations, 6 unknowns. And I've got the, let me close this one as well. Okay, so I've got the time points. Those are the 4 time points, and then also my n matrix right here. So I was given those. So let's go ahead and put those in here at the beginning. I'm just going to copy these and just run these and just make sure that I can print out. Okay, Shift Enter will give you a new cell, and then I can print T, time I guess, not T. Okay, so there are my time points, 0, 0.28, 0.72, and then 1. So those are going to be my collocation points in time, and then I have my n matrix as well that you can just see there. All right, so I have those available to me. Now I just want to set up these equations and variables, and so what I'm going to do is do from scipy dot optimize. I'll import Fsolve. All right, that's the very first thing that I need is this package Fsolve. All right, and then I'm going to define y naught equals 5. That's my initial condition. And then I'm going to have my z guess value. I'm going to set up a that as zeros. So I'm just going to guess that those are all zeros. These are my 3 y1, y2, y3, and then my 3 derivatives. So I'll just start with a 0 guess. And then I need to define a new function. Okay, I'll just say FCN, and that's a function of z. And then I need to break out z. The first 3 are going to be the y values, and then the next 3 are going to be the derivatives. All right, I'll do 3 to the end. Okay, now up next I just need to store the residuals. So I'll do empty and 6. All right, and then F0 to 3. That one is just going to be equal to, I'll do the equation on the right first. Okay, I'll do the dot product of n and dy, and then I'll subtract y minus y0. Okay, that's the first equation. And then the second equation is just going to be, I have to put everything on one side of the equation, and that's going to be 3 to 7, or I can just leave that 7 off there. 3 to the end is going to be dy plus y. So I just had to move everything onto the other side of the equation. All right, and then I need to return f. All right, if I just print out my initial guess, with my initial guess, I'll just say, what's FCN of Z guess? Oh, let me go ahead and run that. All right, so these all need to be 0 in order to satisfy those equations. So now I'm going to have this Fsolve that's going to then iterate for me on starting with the guess and coming up with the successful solution where all 6 of those are equal to 0. Those are the residuals. So what I need to do is just z equals Fsolve, and I'll give it my function name, and I'll give it my guess values. And then I'll just print out z. All right, so you can see the 3 state values. Now those are going to agree fairly closely with what we got here as well. And we can print these out too. Let's just say we have print, let's do R, Y. Okay, so those are similar. I used a little bit different N matrix, a few more digits of precision to get more accurate results here. Okay, but you could derive those as well. All right, so very similar to the results that are right here. Now you'll notice you have 3 other values here. Now those are the derivative values. And it makes sense that they're just the negatives of these values because the equation is right here. You have dy dt equals negative y. So the derivative equals the negative of the state value. All right, so we've computed this both with Fsolve, so solving the orthogonal collocation on finite element equations ourselves, or also with Gekko to do it for us in an automated way to spit out just a little bit more detail beyond what it typically does, which is this is the method for solving it where it solves it automatically for you. Okay, so let's go back to the presentation. All right, so the next exercise is going to be solving a differential equation, not a linear one. Now it's a nonlinear equation, but this u value is just equal to 4. So you still have one variable, one equation that you're trying to solve, and you want to identify the 6 unknowns at the node points. See if you can do that. Okay, you have x1 and the derivative of x1, x2 and the derivative of x2, x3 and the derivative of x3. You want to list the 6 equations. So we're going to have the differential equations that have to be solved at every node. And then you also have the collocation equations that relate the derivatives to the state values. Okay, and you're going to set up and solve those 6 equations and 6 unknowns. And if you go to this link, you'll be able to see the solutions as well as the problem statement. Okay, and so this is going to be the solution when you have anywhere between 2 to 6 nodes. So you can see the different collocation points based on color. You can see the one that's least accurate here is nodes equals 2. So you can see that right here, nodes equals 2. Now, one of the things with this is that if you have fewer nodes, the solution is faster. If you have more, the solution is going to be more accurate. So many times there's just this trade-off between solution speed and accuracy. You typically need just as many nodes as you need to get the accuracy, but not too many to slow you down for the computational time. All right. So there it is with the solution, and hope you enjoyed this video and the course content.